So let's begin with a word of prayer. I'll start. Dear Father, we thank you for your love for us and for creation and for everything you provide for us every day, Lord, even when we don't understand all the things that you do for us each and every day, Lord. We just thank you that you're an awesome God and you love us like you do. Let's pray to be with us today. Help us to understand the nooks and crannies of Fourier Series, that we would be able to understand these theorems and also why they're true. Amen. All right, so as you are aware, we talked about Fourier Series, but I'm not going to post that because nothing good came of it. So we'll leave this one in the record. But basically, this is a Fourier series, right? It's a sum of sines and cosines, and we're looking at a Fourier series for minus L less than or equal to x less than or equal to L. And so there's a couple different variations on this that you can do, right? So like basically, as we talked about last time, if you're given a function, you can extend it periodically, right? So let's see here. There's two different kinds of extensions for the most part, right? Like here's x, for example. Right. Let's say f of x. So that's given, right? Suppose from 0 to L, and then you can either talk about its odd extension or its even extension. So the odd extension would be just, oh man, sorry, too small. He says you need to do at least 3 periods to understand it. I guess that might be true, I don't know. But here's the odd extension, like that. Something like that, all right? And actually, as I was telling you guys, the nature of the Fourier expansion is that for, of course, so here I'm supposing that this is given, this function is given from 0 less than L, then we construct a Fourier series based on the odd extension. Let's see here. So basically the odd extension of that is just itself, so it's kind of hinky. But that would be, now that so-called odd extension, it's going to just be something like f of x equals to the sum, bn sine of n pi x over L, right? Okay, so like this one, we can straight calculate the b sub n. B sub n's by the basically the orthogonal arguments we went through. Oh man, maybe see that part of what we talked about last time is worthwhile. The orthogonality aspect of it. Maybe I hate to post it because there's anyway. So b sub n is, what is it? We figured it out. It will be the odd extension of f. I think we do 2 over L, integral from minus L to L. In this case, x sine of n pi x over L dx, right? In fact, he defines, Haberman defines the coefficients a naught, an, and b sub n by what? He says a naught is equal to fundamental. I wrote these things down so that I can write them down again for you guys. Where did I put that? Aha! So we have a sub naught is equal to 1 over 2L. So this is how basically what he's doing here is he's defining the Fourier series generated from f of x, right? In the same way you can define the the Taylor series generated by a function that's smooth in terms of its derivatives evaluated at points appropriately, right? In the same way you can define a Fourier series by these integrals. The integrals give you the Fourier coefficients, in terms of these integrals of f of x weighted by either cosine, sine, or just a constant, or just itself, right? So this is definition right now, okay? What I'm writing for Haberman, these are definitions. This is how he's defining these coefficients. Okay. So this gives us, when these integrals exist, right, it gives us a way to define. I think I need to zoom in on that a bit. Ooh, wrong way. Yeet. Sorry, I don't do my own camera work very well. Yeet. So those give us the definition of the Fourier coefficients generated by f of x. Of course, we're assuming that, in fact, those integrals exist, right? They don't have to exist for plenty of functions. That's true. All right, so what's going on here is, if you look at the odd extension, right? Let me do this in color a little bit here. So this is the given function, right? And then we're looking at its odd extension. To that, you look at the odd extension, calculate the Fourier coefficients for the odd extension. That gives us what's called the quote-unquote sine series, as he calls it, the sine series. All right, so like this we can do. So let's just do this. We should do some calculation in here, since I'm not like super tired today. So 2 over L. This is straight up integration by parts. So that's like L x over n pi. The integral of sine is minus cosine, so I got a minus. I got myself a cosine. N pi x over L. Plus the integral L over n pi. Integral 0 to L, or minus L to L rather. Cosine n pi x over L dx. Of course, this guy is evaluated from minus L to L. Now this is dumb. I'm not exploiting what I should, which is the fact that this is an even function, right? Product of two odd functions is even. X times sine is an even function. So I'm making work for myself here by doing that. This way, I should have been smarter, of course. Oh, and look, I've got a bogus too, right? What was the definition of Bn? Right. This definition, of course, is made so that, well, we don't have to explain why the definition is made later. We're going to talk about Fourier's theorem, which will explain why the coefficients are chosen the way they are. And so, actually, we've talked about that in previous meetings. So, but, excuse me. All right, so, of course, this we could rewrite as by, that's really, I guess I made my bed, I'll lay in it. No, I don't want to. 2 over L. And instead of minus L to L, it'll go from 0 to L, right? So that times minus L, L over n pi cosine n pi, right? And then like the zero bound gives me 0 because there's an x here. This is an integral of cosine over a full cycle, so that's just 0. And this is it. So what we got, L's cancel. You're left with 2L over n pi minus 1 to the n plus 1. Because cosine of n pi is minus 1 to the n. Right? So after this little song and dance, we figured out, in fact, we can erase that v sub n and replace it with a much more specific 2L. Oh, this marker's not very good. Let me find one darker. 2L over n pi to the minus 1 to the n plus 1, and then again sine of n pi x over L. this is the so-called Fourier Sine series for f of x equal x on 0 less than or equal to x less than or equal to L. It is also the Fourier series of the odd extension of x from minus L to L. And then it repeats over and over and over again, right? And the thing that's interesting is on the jump discontinuities, right? It's actually taking the value in the middle, right? Talked about the average of the left and the right. That's where the Fourier series will converge to. All right, so that's the one thing we can do with x is we can look at the odd extension, right? But there's another thing you can do. You could look at the even extension, right? So the even extension of this guy would be something more like, so we've got what we're given, right? And then even extension looks like this, right? And then it repeats. Right? All right, so again, let's see here. Here's your L, here's your minus L. In this case, the average of the endpoints is just that, right? So the even extension, the periodic extension of the even periodic extension is continuous, in fact. Right? This one's not continuous, as you can see. Right? The extension's not continuous, but here, this is a continuous, as it happens, extension. And so, yeah.
Sorry. Did you just say that was just the odd extension, or was that the odd with the even extension?
This is the even extension. Even periodic extension. Of
Oh
f
yeah,
of x
we just did the sign thing.
equals to x. Oh, by the way, you know, the a sub naught and the a sub n were 0 over in our first extension because those are both odd integrals over about a symmetric, right? In contrast here, the b sub n is 0 because we're integrating this even function. You know, you put an even function here, the total thing is odd, so this is 0, whereas this and that are non-zero. Let's calculate them. So the, let me, well, I hope my camera work probably leaves something to be desired near. Oh well. I think eventually I'll get to everything that I'm supposed to, but it might require some patience on the part of the watcher. Sorry about that. Alright. There we go. So, here, again, we have that the b sub n is equal to 0 by odd integral is 0 argument, right? The a sub naught is equal to 1 over 2L the integral from minus L to L f of x dx, right? But f is even, so this is really 1 over L, the integral from 0 to L of f of x dx, right? That's how we should do it. Because it gives us no joy to integrate from minus L to L when we could just integrate from 0 to L. Now that is just x, right? Integral of x is x squared over 2. Let's see here, so that gives us, looks like L over 2. Now, the a sub n, I'll just go ahead and do the doubling. We'll get 2 over L, the integral from 0 to L. Then we got ourselves an x cosine n pi x over L dx. Again, integrate by parts, 2 over L. And this time it gives you L n pi x. Oops, sorry, can't do math. Integrating reciprocates the argument of the cosine, right? So we get Lx over n pi sine n pi x over L, evaluate from 0 to L. Hardly worth quibbling over though, because that's 0, minus L over n pi, the integral of sine n pi x over L dx, 0 to L. Now this guy is actually going to give me minus L over n pi cosine n pi x over L. And you got to evaluate that thing from 0 to L, right? And so what's that give us? Well, that gives us, this piece goes away, and what you got then, these L's cancel, so you're left with 2L over n squared pi squared, and then cosine, so it gives you, the upper bound gives me minus 1 to the n, the lower bound gives me 1. Now if you think about that for a second, you see for even n it's 0, right? So in fact we can even do a little sneaky stuff here and say a to the 2k plus 1 is equal to what? Maybe I should do it here. A to the 2k plus 1 is what? A to 2k is equal to 0. Because if n is even, if n equals 2k, this is 1 minus 1, 0. But if it's 2k plus 1, then you got 2L over 2k plus 1 squared pi squared, and then that's just 2, right? So 4. So in fact, with that little bit of arithmetic behind us,
-2?
minus, thank you, yeah. A little bit of arithmetic behind us, we have that f of x is, well, it's not f of x though, is it? We shouldn't really say f of x is equal to this. What we should say is the even extension of f, right? Is equal to, what was our a sub naught? L over 2, right? Minus the sum k equals, I guess k equals 0 to infinity. Because if I k plus 1, 2k plus 1 starts at 1, right? So I start at k at 0 if I start at 1. And 4L over 2k plus 1 squared, pi squared, and then what was it? It was cosine of n, or rather, excuse me, not, what is n though? Cosine of 2k plus 1 pi x over L. And that, my friends, is the Fourier series, the Fourier cosine series as it's known. This is the Fourier cosine series. For f of x equals to x on 0 less than or equal to x less than or equal to L. as you can see, these are quite different series, right? They both match f of x equals to x, right? On the what? Between 0 and L, right? But they're Fourier expansions for different functions in the extension, right? Like I said, one is the even extension, the other one's the odd extension. One is continuous, the extension is continuous, the other one, the extension is odd. Is discontinuous, rather.
So I'm kind of confused by the whole like interval thing, but like with L, like so say we have a function and we do want to kind of like approximate it. Is there something special about like choosing an interval L, or are we just
Okay, so
we allowed to have pretty much any ultimate freedom?
So remember we looked at the heat equation, for example, with particular boundary values. We found when we worked it out with respect to those boundary values that I want to say it was sines. Sines were solutions because we had to how did it go? Curses. Oh man, I wish I could remember what we did. Remember with the heat equation, we looked at that. Yeah. And I think we worked through it, and when we worked out the boundary value problems, we found that the sines, we had a series of sine, like every sine of n pi x over L, functions like that solve the boundary values, right? And they were like, oh, so if we write our initial condition as a sum of sine functions, then we can equate, like we can make a general solution that matches the initial condition using the sine functions, right? But that's because we were looking at a heat equation with like, I think it was fixed. It was like fixed temperature 0 at the endpoints, right? Now, if in contrast, if you fix the if you insulate the ends, I think, and you like keep, how's it go? I want to say you do 0 derivatives at the end. We work through that boundary value problem. You get a cosine series. So there you would want to use. Actually, you want to use a Fourier cosine expansion to sort of rip apart your initial condition function to match the general solution that's possible for your boundary value problems. So which one you want to do depends on the PDE you're looking at.
Okay.
But you got options, right? Like for a given function from 0 to L, we can either look at its odd extension or its even extension most naturally. Those give us the so-called, by definition, the Fourier series for the odd extension is the sine series for f of x, and this is the cosine series for f of x. And at least that's in excuse me. I think that's what Haberman defines. Now, of course, you could do other extensions, right? Like, what if you extend the function to be, like this? Well, if you do that, it's neither one of these. It's actually going to need a sum of sines and cosines to get that. Right.
Okay.
But he actually explains if you're finding the Fourier expansion of a function which is neither even nor odd, he does make connections with the sine and cosine series for the odd and even parts of the function as well. If you read the chapter carefully, it's in there. I may get to it. Let me see here.
Okay. I think that makes a little more sense.
Yeah, maybe. I know there's a lot of flavor options, so to
Yeah.
speak, here. That's what you get lost with. The question is, what are you trying to do, right? Like,
Yeah. So, I mean, it kind of makes more sense because, like, I mean, at least like graph of the equation from like negative L to L, it kind of seems like how you pictured it like before in the heat equation problem, like starting at like kind of like 0 in the center.
yeah,
And then it's at a certain fixed temperature at the ends.
yeah.
But I think.
Yeah, well, for one thing, this would not be a legitimate initial condition for the heat equation problem because it doesn't have zero temperature over here.
Yeah.
So we wouldn't have tried to find the.
I was looking at the other graph, like right there, but I guess maybe it would be flipped too.
Um,
I'm not sure.
in any event, there's a couple of sample calculations for you. Now the Fourier theorem, what's it say? It says basically the Fourier, if it says if f of x is piecewise smooth, all right, from minus L to L, so it could have some jump discontinuities, all right, then the Fourier series of f of x converges to the periodic extension of f of x. And what that means is it just matches f of x where f is continuous, and on jump discontinuities it gives you the average of the left and the right limits, usually. He says usually. But he doesn't.
Usually.
I know, that's very troubling to me.
It's an uncomfortable word. Wasn't from the other day, it just said, like, always. Wasn't it?
I think he says usually. I don't know if he's writing this, maybe he writes that because there's sometimes when it's just, when they're equal. I mean, it could be that kind of language he's using, right? Like, I mean, I would say that it's still the average of the left and the right here. Yeah. But maybe he's talking about this for a less intelligent audience. I don't know.
Let's start using that in proofs.
Yeah, just throw in some
usually.
Just throw in some usuallys. Yeah, I'll take points off for that. Let's see here.
It's 5:00 p.m.
Shut up. Sorry. Okay, so.
Put a clock.
So we found the Fourier sine series and the Fourier cosine series for x. Those are useful examples for us because. Let's see here. All right. Talked about Gibbs phenomenon, right? Last time a little bit. Let's see here. Well, anyway, the things that we talked about last time in the lecture I'm refusing to post, we will again talk about in later lectures for those who are following along beside you guys. Anyway, where was I? Oh, he finds the Fourier sine. This is actually an interesting example. He has on page 100 to 101. He finds the Fourier sine series of cosine pi x over L. Let me just put it over here for the moment. I think that might actually be helpful just to get a little bit more sense of what's going on here. We'll put it over here. So he's like, to find the sine series for f of x equals to cosine pi x over L. So let me just show you graphically what this means. Okay, so what does cosine look like from 0 to L? Starts at 1, right? And when you put L in there, what do you get? Cosine pi? That's -1, right? So basically we're looking at one of these deals. So the sine series is the odd extension of this. So what's the odd extension of that? It's right. Wait a minute.
That's an even.
I can't do math.
That's just finishing sine.
I was like,
cosine.
that's the even extent.
It's like, how do we do this?
Oh, by the way, so that's the even. That's actually a good point. What would the even extension of this be?
That.
That itself. And then find the Fourier cosine series for this function. It is its own Fourier
Yes.
cosine
Yeah.
series. Right. That's kind of like being. It's like the punk question in Calc 2 that we always ask students just to mess with them. Like, find the Taylor series for this third order polynomial.
It's just the third order.
It's exactly. I guess to make it fun though, we usually ask we ask to find the Taylor series centered at some place other than 0, and it actually feels like you're doing something, but you're not. Anyway, so. Right. So here's the. I'll make it dotted. Here's the odd extension, right? And then the Fourier just keeps repeating, right? Et cetera, et cetera, et cetera. I'm just gonna draw that much. But we know what happens because of the jump. Actually, the series is going to converge to this value, and this value, and this value, and this value, and so forth and so on, right? But it'll be 0 at the jumps, because that's the average of 1 and minus 1. All right, so so then f of x sine series, right? So it's like the sum n equals 1 to infinity, b sub n sine of n pi x over L, and to find the b sub n's, you calculate the integral. All right, so usual even odd trick. The integral we're looking at is an even integral, so instead of minus L to L, we do from 0 to L. We multiply by 2 over L in the definition that I wrote on the other board a second ago, and so then you just kind of iterate like cosine pi x over L sine n pi x over L. Product of sine and cosine is what?
Euler knows.
Do not remember.
Don't remember. Yeah, me neither.
Right.
Cosine theta sine beta is 1 over 4i e to the I theta minus, plus e to the minus I theta. Sorry, Cooper. E to the I beta minus e to the minus I beta. Actually, I don't know if I can. I don't think I see that from a stupid camera either. Am I off the side of the world? A little bit, yeah. Oh, I just barely fit it in there. All right. Anyway, so I'll write over here so you see it. So that's 1 over 4i, and you got e to the I theta plus beta minus e to the minus I theta plus beta. Minus e to the I theta minus beta, parentheses minus e to the minus I theta minus beta. Okay, fine, whatever. Anyway, that's 1/2 sine of theta plus beta minus 1/2 sine theta minus beta, right? So this is really the integral from 0 to L. Why am I doing this? I didn't want to do this today. The sine, there's 2's cancel, trigonity. Sine of n plus 1 pi x over L minus the sine of n minus 1 times pi x over L. Why am I working this out? I didn't want to do this. I'm wasting precious time doing this. I'm sorry, guys. You guys could figure this out. Oh well, this far in, we finish it. So what happens to these integrals? How there's not 0? Oh no! Oh no! Oh, not cool. Huh. Hmm.
What to say to cancel? I mean, no.
I get a cosine. Maybe I'm wrong. Oh, I'm wrong about them automatically integrating to 0. Sorry about that. So this, I'm an idiot. This is 1 over L. And what you got here is, the L's cancel. Let's get rid of them. So 1 over pi times n plus 1 cosine n plus 1 pi x. There's a minus evaluated from 0 to L plus 1 over pi times n minus 1 cosine n minus 1 pi x from 0 to L. So, what this is, right? It's 1 over pi. That's everywhere. And you got yourself a...
Wait, I think you took the L's out of the trig functions.
Well, when I
They
integrate,
cancel.
the L outside and the L inside cancels in the substitution. So this is oh, you're right. I know what you're saying.
Of the angles.
You got me, Jess. Very good. Yeah, that's important because that
Yeah, they cancel out
Cancel.
the integer multiples of pi.
So we got ourselves minus 1 to the n plus 1. There's a minus out here still. Don't forget about that one. And then minus 1. And then all divided by n plus 1. And then 1 over, let's find pi times n plus 1, and minus 1 rather. And then this over here is minus 1 to the n minus 1. Minus 1. So then what you do is make a common denominator, right? So we're going to do, first of all, let me clean up just a little bit. This is 1 over pi times n plus 1, right? Upstairs, I got myself a 1 minus 1 to the n plus 1. All right, I just multiply the minus through. And then over here, 1 over pi n minus 1, fine. Minus 1 to the n minus 1. I mean, I could say n plus 1 just the same, make it all nice and pretty. I don't know, whatever. I just made it n plus 1 because I want to. Now they look the same, sort of. And then make a common denominator. 1 minus 1 to the n plus 1 times n minus 1 plus n plus 1 times minus 1 to the n plus 1 minus 1, all divided by pi times n squared minus 1, because n plus 1 times n minus 1 is n squared minus 1. Oh, there's a common. Look at that. This is common. Both places, right? I could have done that up here, right? I could have just been like 1 minus 1 to the n plus 1 over pi, right? And then said that it's 1 over n plus 1, right? Minus 1 over n minus 1. That's a nicer way to look at it, isn't it? Yeah, let's do that way. Forget this common denominatoring. Dummy. It's dumb. This is easier. It's the same animal. I mean, forget me. Just you do it. You get it. You know. So this is 0 for n even, right? Or is it 0 when it's even or odd? Which is it? Even 0, right? Yeah. And for n odd, let's see here. Let me just do it over here right quick. 1 over n plus 1 minus 1 over n minus 1 is what?
Minus 2 over n squared minus 1.
You said it's 2n over n squared plus 1?
No, it's n minus 1 minus n minus 1. So it's just negative 2.
Oh, just 2.
Negative 2.
Negative 2?
Yeah.
Oh, okay. So that's that. But then this is also... No, that's 2. So we get minus 4 over n squared minus 1 if n is odd, right? Sorry, that was not my intent. I should have... Man, I was going to bail after I drew the picture. What an idiot. Anyway, there's how you calculate the Fourier coefficients for the cosine in terms of the sine. Alright. Moving along here. Let's see here. Let me read this little discussion. It may be apparent that any function f of x, which is piecewise smooth, may be represented both as a Fourier sine and as a Fourier cosine series. The one you would use is dictated by the boundary condition. Boundary conditions, all right. So it's also possible to use a Fourier series including both sines and cosines.
That's what you were just saying about like.
Yeah, so like on page 105, he does something kind of like that,
Yeah.
but for his own little bit. And now he's talking about even and odd parts here. What's the story there? What's his takeaway message here? The Fourier series of f of x equals to the Fourier sine series of the even part plus the Fourier cosine series. Excuse me. Okay. Alright, so here's the connection between, here's the, it is very simple really. Let me just write it out. Once I write it, you guys are like, oh, okay, no big deal. We can get rid of this, I think. Yeah. Anyway, I hope this integration helps you guys as you look at specific problems in your homework as we go on here. So it's probably not time wasted actually. So here's the deal. Generic f of x, right? So this is for, this one is on minus L less than or equal to x less than or equal to L given. We can rewrite this standard trick, right guys? 1/2 f of x plus f of minus x, right? Plus 1/2 f of x minus f of minus x. So this is called the even part, or he just calls it f sub e for even. And this is called the odd part, or just the odd part of f. Have you guys ever seen this before?
I think you showed it to us in linear before, kind of with the matrices.
I usually sell this in calculus as an explanation of where Cauchy and Singe come from. You know, an application of this, a very nice application is e to the x. 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. We'll check it out. That's Cauchy.
Plus Singe.
That's Singe. They're respectively the even and odd parts of the exponential function. Anyway, here's the story. So the question the Haberman poses is, what's the relation between the Fourier, full Fourier series for f of x and the sine and cosine series for f of x. And that of course is, and this is by definition, right? That's 0 less than or equal to x less than or equal to L, right? I mean, basically the Fourier sine and cosine series are just based on the part of f, which is from 0 to L. Well, here's the relation. The sine series is the Fourier series of blank. The cosine series is the Fourier series of blank. And the full Fourier series is blank. Just fill in the blanks. So basically just this, the Fourier series of f of x equals the Fourier sine series plus the Fourier cosine series. So oh, I've not said it right. Curses. This is backward. I got it backwards. I've asked the question the wrong way. There's no good answer to my question. What's the relation between the full Fourier series? Oh. Sorry, I'm wasting precious time with this very only moderately interesting comment about what we're doing. Here it is, though. The full Fourier series is equal to the Fourier sine series of f, the odd part, plus the Fourier cosine series of the even part. He says, please do not confuse this result with even and odd extensions. For example, the even part of f of x is 1/2 f of x plus f of minus x, while the even extension is, that's actually a pretty good point. Even extension, actually this is a very useful comment. It's probably something I would end up getting confused about before I realized it. Even extension of f of x is what? It's f of x. If x is greater than 0, it's f of minus x if x is less than 0. You know, this is of course for, I mean, fine. I mean, we're limiting it between, let me just add some fine print here. Anyway, there.
Can you say that part again? Don't get the confused with.
So this is not at all the same as the even part of f. Right? The even part of f is up here. So like contrast this with that. So for example, just to be more specific, exponential function looks like that, right? The even extension of the exponential function is that guy.
Mm.
The f sub e is f sub e is something different. It's like it's roughly speaking. I mean, here f sub e is equal to e to the x plus e to the minus x over 2, whereas and so this e to the minus x over 2 piece is getting dinky. right, as you go over here, whereas the orange one, the exponential, this is y equals e to the x. This guy over here is y equals e to the minus x. Those are different functions. The orange is the even extension, the purple is just the even part of the exponential function, which I haven't graphed yet, by the way. The exponential function, you know, goes on like that, right? So anyway, they're different things. All right, so moving along. We got to the interesting part. Sorry, guys. So the continuity actually is important here. You know, we get used to we give lip service to continuity at the start of things in calculus, but it kind of doesn't play that big a role in a lot of what we do. I mean, at least it doesn't feel that way to me computationally, right? There are plenty of students who can do pretty good calculus and don't understand a lick about continuity, right? Maybe they, I guess some people would argue that they're not really that good at calculus, but whatever. You know what I mean. So here's he says it's worthwhile to summarize the conditions under which a Fourier series is continuous. For a piecewise smooth f of x, Fourier series of f of x is continuous from minus L to L if and only if f is continuous and f of minus L is equal to L. So if you think about about what we've described in terms of how the Fourier series behaves at jump discontinuities, this makes sense. So basically it's going to be continuous if there's no jump in the middle, right, where it just keeps repeating itself. And in the different windows where it gets glued together, it has to glue together without a jump. So that means that f of L has to be equal to f of minus L. So for like up here, not continuous, continuous. See, f of L is equal to f of minus L for this one. So in particular, the Fourier cosine series is automatically continuous because it's built from an even extension which builds in f of L is equal to minus f of L. Like he says next. Fourier cosine series of f of x is continuous for 0 less than or equal to x less than or equal to L if and only if f of x is continuous. For piecewise smooth f of x, Fourier... No. Right. Okay. And then, again, for piecewise smooth f of x, functions f of x, the Fourier sine series of f of x is continuous for 0 less than x less than L, if and only if f of x is continuous, and, I mean, it's kind of funny, like he's talking about piecewise smooth functions, but he's not really talking about piecewise smooth functions, because he shortly thereafter adds they're continuous. Well, if they're continuous, they don't really have pieces. I mean, I don't know, there's something kind of funny about the way these are stated, but it's fine, it's fine. Anyway, basically, again, the sine series is going to be continuous only if f of 0 is equal to f of L. That's for example, not the case here. So in order for a sine series to be continuous, we'd need something that looked more like, oh, I'm sorry, I keep pointing at things in that. Well, anyway, I'll just say it. I mean, you'd need something that comes back to where it started, like a tent function or something, you know, that started at 0, went up to something, and then came back to 0 at L. All right. That language is important because that's needed to state the more interesting theorems here. Term-by-term differentiation of Fourier series. Finally, we're getting to the good part. The thing that we did wrong in the class that need not be posted is that we just tried to dive straight to here without appreciating the distinction between even extension, odd extension, full Fourier series, right, and the interplay between them. All of that is important to completely understand the story he's telling in this chapter. Specifically the continuity, right? All right, so, you know, he looks on page 112 to 113. Basically, he looks at the heat equation. He goes through the same thing we went through, basically shows you get a formal solution of sine n pi x over L, and then he's like, if you differentiate with respect to time, differentiate with respect to x, you're going to get a solution if you can pass the partial derivatives inside the series, the Fourier series. That's not quite the way we looked at it, but it's kind of looked at it the other way around, but it's essentially the same thing. We solved things, and we added them. We used linearity to add solutions together. He's constructing a series, and then plugging it into the differential equation to show it works. But they're logically connected. These ideas. Anyway.
So wait, why can he differentiate there and we can't?
Oh.
Didn't we have problems when we differentiated the function before?
We just looked not at we looked at finding a specific function which satisfies the boundary condition, and then we argued that if we had two of them, we could add them together, and we'd still satisfy the boundary conditions because the boundary conditions were homogeneous. 0 plus 0 is 0. And then we got really greedy, and we said, well, if we can do it twice, we can do it infinitely many times. So let's take an infinite linear combination of these solutions to the boundary value problem. That led us to a Fourier type expansion of our solution.
Mm-hmm.
It's a little bit different though, because it also had time in it, right? We had the exponential times the sine.
Yeah.
Each one of those things solving the heat equation, and then the problem was we had to fit the the initial condition. So I'm just trying to say what he does on page 112 to 113 is really just kind of the same. It's the same idea, just in a slightly different order of operations, all right? It always comes back to this. Can you... Well, for us, is the sum of solutions again a solution, I guess? I think his way is a little more logical. Basically, he's like proposing a solution, and then he's trying to plug it into the heat equation and see if it works, right?
For the heat equation, it would work because it's a linear partial differential equation.
Well, it would work if we can actually commute the summation with the differentiation.
Mm-hmm.
When is it possible to differentiate term by term? Is the question really? Now he gives us, so basically here's the let me show you the problem. you gotta read page 112 and 113 to understand what I'm getting at here. We've dodged this discussion by kind of going at it at a different angle, all right? But I mean, here's the problem. I'll write it out. So he's like, he's got u of xt equal to sum n equals 1 to infinity of b sub n sine of n pi x over L e to the minus n squared pi squared over kt over L squared, right? And he's like, so if you can calculate partial u, partial t, and you can calculate partial squared u, partial x squared, and you can see that this solves ut equals to k uxx. But in order to actually make that, in order to make that claim actually, legit, he has to do something. All right, in order to actually see this, he has to be able to do this step.